Hi, this is Madhu. In this video, I'm going to discuss how to reduce the number of states in a finite automata. We can also call it as minimization of DFA. For a given language, there can be many DFAs that accept the same language. Though all those DFAs were equivalent, there will be difference in the number of states in such automatas. Considering the simplicity and storage efficiency, the DFA that is having less number of states is always preferable over the other DFAs. For example, let us consider two DFAs which are equivalent and accept the same language, that is the given language. Here, figure 1 and figure 2 both accept the same language. But if we see, figure 1 has 6 states in it and figure 2 has only 3 states in it. So, which reduces the space. Now in figure 1, if we see, there are certain states which are redundant and certain states which are not useful or not accessible from the initial state. For example, state Q3 and Q4 are marking the final states and they are redundant also. And state Q5 is not accessible from the initial state. So, such inaccessible states can be removed from the DFA, and also the equivalent states can be put together so that an equivalent DFA with less number of states can be formed. So to identify which are the states that are equivalent, we need to understand the following definitions: distinguishable states and indistinguishable states. Distinguishable states is that in a DFA, when we consider two states, say P and Q, if one state belongs to final state and another one belongs to non-final state or vice versa, then we call those two states as distinguishable states. And indistinguishable states is that if both the states in a pair belong to final states or both the states in a pair belong to non-final state, then it is called as indistinguishable states. There are many algorithms available for reducing the number of states in a DFA. One such method is this mark-reduce procedure. This method is basically based on finding and combining the indistinguishable states. So let's start with the mark procedure. This is used to find the pairs of distinguishable states. So first we are going to mark which are all the distinguishable states, and also at the end of this procedure we are going to have an equivalence class with states which are all indistinguishable states. The first step in this procedure is to remove all inaccessible states. The meaning of inaccessible states is that any state that cannot be reached starting from the initial state. For example, in the given DFA, from initial state Q0, Q1 can be reached, Q2 can be reached, from Q0, Q3 can be reached, and then from Q0, Q4 can be reached. Whereas Q5, this state it cannot be reached from the initial state. So this state is called as the inaccessible state, and we can remove this state from this DFA. As we remove this state, we can also remove the transitions that are associated with this state. So after removing the inaccessible state, that is Q5, we have got the DFA as follows. And the transition table for this DFA is given here. So the states that are available in the DFA is given in the column, and here the inputs that are present in the DFA is given. So Q0 on reading 0, it goes to state Q1. Similarly, Q0 on reading 1, it goes to state Q2. So by this way we can fill this transition table. The next step is to consider all pairs of the states. And in every pair we need to identify whether that pair is distinguishable or not distinguishable. So if one state belongs to final state and another one belongs to non-final state, then that pair can be marked as distinguishable. And also at the end of this step, the state set is partitioned into non-final and final states to get the equivalence classes. So let's continue with the given example. After removing state Q5, which is an inaccessible state, the states available are Q0, Q1, Q2, Q3 and Q4. Now with these 5 states, the possible pairs that can be made are the following: Q0, Q1, Q0, Q2, Q0, Q3, Q0, Q4, and then again Q1, Q2, Q1, Q3, Q1, Q4, and again Q2, Q3, Q2, Q4, then Q3 and Q4. So these are the possible pairs of states that can be formed out of these states. Now, in these pairs of states, we need to identify which are all the pairs that can be marked as distinguishable. So to mark as distinguishable in a pair, one state should be final and another should be non-final. So let us take the pairs which are having the final state, so that we can easily identify whether that is a distinguishable state or not. So in the first pair there is no final state and both belongs to non-final state. So this is not a distinguishable state. The second one, again, there is no final state in it. Both the states Q0 and Q2 belong to non-final state. And the third pair, if we see Q0, Q3. So in the given DFA, if we see Q3 and Q4 are marked as the final states. So here Q0 belongs to non-final state and Q3 belongs to final state. So this pair can be marked as distinguishable state. And again, in the next pair, Q0 belongs to non-final state and Q4 belongs to final state. So this also can be marked as a distinguishable state. The next one is Q1, Q2. Both belongs to non-final state. So this cannot be marked as distinguishable. And here Q3 is final state and Q1 is non-final. So this is distinguishable. And again Q4 is final state and Q1 is non-final state. So this is distinguishable. And again here Q3 is final, Q2 is non-final, so this is distinguishable. And here Q4 is final and Q2 is non-final, so this is distinguishable. Here both the states were final states, and so we cannot call it as distinguishable states. So after marking these states as distinguishable states, here we are generating the equivalence class out of the states available. So we are considering two classes here. One class contains all the states that are non-final, and the other class contains the states that are final. So this is non-final states put into one class and final states put into another class. So the step 3 is repeat. We are going to identify which are all the states that are not marked in the previous step. So there are certain pairs which are not marked as distinguishable in this step. So in the third step, we are going to check whether any more states can be marked as distinguishable. So for that, for all the pairs that are not marked as distinguishable in the previous step, we are going to compute a transition function for all alphabet, like transition function that is delta of p comma a and delta of q comma a. So that will yield another pair, and we are going to check whether this pair can be marked as distinguishable. If this pair can be marked as distinguishable, then we can mark the pair p comma q also as distinguishable. Let's continue with our example and see how it works. The remaining unmarked pairs after the second step are these four pairs: Q0, Q1, Q0, Q2, Q1, Q2 and Q3, Q4. Now consider the first pair Q0, Q1. So the input alphabet that is available is 0 and 1. So first take the input alphabet 0 and apply to both these states. So transition of Q0, 0 is Q1, as we see in the transition table. For our easier reference, I have given the transition table here. So Q0 on 0 is Q1 and Q1 on 0 is Q2. So this yields a pair Q1, Q2. Again, we apply the input symbol 1 to both the states. Q0 on 1 is Q2 and Q1 on 1 is Q3. So this yields another pair Q2, Q3. Now in these two pairs, check if any one is distinguishable or both are distinguishable. Q1, Q2, here both belongs to non-final state. So this pair cannot be called as distinguishable. This is indistinguishable state. Whereas this pair Q2, Q3 is called as distinguishable because Q2 is non-final and Q3 is final. So since one pair of these states has said to be distinguishable, we can also say that this Q0, Q1 is also distinguishable. So next consider the next pair Q0, Q2. It is taken from here, Q0, Q2. So again apply both the inputs 0 to the states Q0 and Q2. Also applies input 1 to the states Q0 and Q2. So when we apply 0 to states Q0 and Q2, we are getting Q1 and Q2 from the transition table. So Q0 on 0 is Q1 and Q2 on 0 is Q2. So we are getting Q1, Q2. Similarly, when we apply input 1, we are getting Q2 and Q4. In this, again, when we consider these two states Q1, Q2 and Q2, Q4, one of them is distinguishable. Since here one is non-final and another one is final state. Since Q2, Q4 is distinguishable, we can say the pair that we have considered, this Q0, Q2, is also distinguishable. So continuing with the same pattern for the remaining pairs Q1, Q2, we are getting two pairs again Q2, Q2 and Q3, Q4, which both remains to be indistinguishable states. Since both these pairs are indistinguishable, we can say this Q1, Q2 is also indistinguishable. Similarly, the final pair Q3, Q4, this also remains to be the indistinguishable state after applying the inputs 0 and 1 and finding the transitions. So after this step, so now we have concluded that among the remaining 4 pairs of unmarked states, now we have identified 2 pairs as distinguishable states and the other 2 pairs are indistinguishable states. Now, whenever 2 states are found to be distinguishable, they are put into separate equivalence classes because they cannot be, since they are distinguishable, they have to be put into separate classes. Now if we see Q0 and Q1 are distinguishable states. Earlier, if we remember, the equivalence classes were 2 classes were there, one class containing Q0, Q1 and Q2. So now, since we have identified Q0 and Q1 as distinguishable, these two cannot be together in a single class. So these two has to be separated. So now taking Q0 out from this class and putting it into a separate class, we get as Q0 in a separate class, Q1, Q2 in a separate class and Q3, Q4 in another class. And Q0, Q2 again has to be put separately. It's already put separately. So at the end of this step, we have generated the equivalence classes as 3 set of classes, one containing only Q0 and another containing Q1 and Q2 and the third one containing Q3 and Q4. So this is the end of the mark procedure. Then comes the reduce procedure. So this reduce procedure is used to construct the reduced DFA. That is to reduce the number of states in the given DFA. So for this, the first step is we need to create the states for the reduced DFA. That can do it by looking into the equivalence class that we have generated. So simply we can take only the numbers in the states and we can create a state using those labels. So we have in the equivalence class Q0 in one state, so we can make 0 as a state and then Q1, Q2 in one state, so that we come together, we make it as 1, 2 as one state, then Q3, Q4, that we make it as 3, 4 as a state. The second step is in the reduced procedure is, in the given DFA, we have transition rules for every state. So here again we need to find the transition rule for the new DFA. So for each transition rule in the given DFA of the form delta of QR, A is equal to QP, find the sets to which QR and QP belong. So for example, the transitions for our reduced DFA will be in the given example is from 0, that is Q0, on reading 0 it goes to Q1. So Q1 now it is belong to state 1, 2. So input 0 it reaches the state 1, 2. Similarly Q0 on 1 it goes to Q2. So again this Q2 it belongs to state 1, 2 in the new DFA. So input 1 also it reaches the state 1, 2. Then Q0 on Q, then we in the actual DFA what it is for Q1. Q1 on 0 it goes to Q2. So here Q2 again remains in the same state. So that we have a self loop over here. 1, 2 on 0 it goes to the same state. Similarly Q1 on 1 it goes to Q3. So here Q3 it belongs to state 3, 4. So on reading input 1 it goes to state 3, 4. So similarly in the actual DFA Q2 on 0 is Q2. So here Q2 belongs to state 1, 2. And on reading 0 it remains in the same state. Q2 on 1 it goes to Q4, so it is going to Q4. Q3 on 0, Q4 on 0 both remains in the same state, Q3 and Q4. Okay, so Q3 on 1 it goes to Q3, so the input 1 remains in the same state. So this is the new transition functions that we need to write for this DFA. And the third step is the initial state is the state whose label includes the 0. So whichever state contains the label 0, that will be marked as the initial state or the start state. And the last step is we need to identify the final states. The final states are the set of states whose label contains I such that Qi belongs to F. In the actual DFA if we see Q3 and Q4 were the final states. So whichever state that contains the label this 3 and 4, that is marked as final state in this new DFA. So by this we have found the reduced DFA for the given actual DFA. Thus the minimal DFA is found using mark reduce procedure. Thank you.